Hello students, let us see about data warehouse building blocks, implementation and physical design process. A data warehouse is a subject oriented, integrated, time variant and non-volatile collection of data in support of management's decision making process. First, let us see about subject oriented. In an organization, data warehouse is organized around major subjects such as customer, product and sales, and is focusing on the modeling and analysis of data for decision makers, not on daily operations or transaction processing. This provides a simple and concise view around particular subject issues by excluding data that are not useful in the decision support process. Next, we will see about integrated. Data warehouse is constructed by integrating multiple heterogeneous data sources such as relational databases, flat files and online transaction records. The data cleaning and data integration techniques are applied and they ensure consistency in naming conventions, encoding structures and attribute measures among different data sources. For example, room rent, tax, breakfast covered are integrated into the attribute measure hotel price. When data is moved to the data warehouse, it is converted into integrated attribute measure. Time variant. The time horizon for the data warehouse is significantly longer than that of operational systems. Operational database, it is nothing but the current value of the data. Data warehouse data, it provides information from historical perspective. For example, data warehouse can provide the details about past 5 to 10 years. Every key structure in the data warehouse contains an element of time explicitly or implicitly, but the key of operational data may or may not contain time element. Next, we will see what is non-updatable or non-volatile. A physically separate store of data is transformed from the operational environment. The operational update of the data does not occur in the data warehouse environment. It does not require transaction processing, recovery and concurrency control mechanisms and requires only two operations in data accessing. They are number 1, initial loading of data and number 2, access the data. Next, we will see what is the need to separate operational and information systems. There are three primary factors for separating operational and information systems. They are: first reason, a data warehouse centralizes data that are scattered throughout disparate operational systems and makes them available for DS. Next reason, a well designed data warehouse adds value to data to improve their quality and consistency. A separate data warehouse eliminates much of the contention for resources that results when information applications are mixed with operational processing of the data. Next, we will see data warehouse implementation for business intelligence, which is nothing but BI. Business intelligence BI and data warehouse DW are separate entities serving distinct functions in the organization. The data warehouse representing the enterprise information architecture serving to achieve a single version of the truth is necessary today to support the user facing BI system in the DW BI solution. Once the operational systems can be completely standardized, reduced to simply transactional data including a history for both master and transaction data, and can put out flawless data, we will be able to run BI tools directly against them. The traditional data warehouse is mostly necessary to support BI. Once the information technology has created, populated and validated the accuracy of the data in the data warehouse, the goal is to enable business users to access and analyze their data without much further IT involvement, yielding self-service BI. Self-service business intelligence sitting on top of quality information should identify result in better business decision making, enabling executives and managers to act. The primary objectives of the data warehouse are data management and delivery. Data management, which includes data analysis, encompasses the bulk of the effort in that it involves standardizing and integrating data from multiple sources. Additionally, the ability to share data and reuse the processes is a major goal of a mature DW/BI environment. Knowing that the data warehouse is tied to BI, there are several components that frame the overall BI initiative. Let us discuss one by one. First, business requirements. The first aspect in establishing a data warehouse and the reason to practically have a BI initiative in the first place is the analysis of business requirements for analytics capabilities. The first challenge is in the prioritization of the strategic analytical requirements, which usually provides the highest return on investment, which is nothing but ROI, over operational reporting requirements, typically providing a lower ROI. Key factors to consider that impact the overall effort and scope of the project include assessing the organizational readiness, effective communication of upcoming changes to all affected, managing scope of users changing their own initial requirements, breaking the project into manageable phases with easily attainable milestones. Next, we will see about data warehouse design. Mapping key business requirements to benefits achieved by BI is where key metrics to be improved upon need to be determined. Beneficial changes to the key performance indicators KPI such as increased revenue, improved profit margin and reduced cost need to be considered in the data infrastructure requirements. A risk mitigation strategy should be built into the overall equation. Business value can be achieved by addressing those high value, high priority BI requirements and translating them into sound data design and or model. Data analysis and administration are a major part of the effort in the design phase, since activities such as data integration, data profiling, data modeling, collaborating with data owners, data governance, data cleansing, resolving data integrity issues and disputes and other custodial responsibilities such as data validations must take place to achieve a robust design. Data anomalies, misunderstandings and disagreements about the data may surface among users, which must be addressed. The first aspect of the database design includes the database design schema, which is documented as a physical data model which shows tables, columns, primary and foreign keys and indices. It is either a star schema or snowflake schema or a relational or non-multi-dimensional schema. The second aspect is the physical design document, which describes dataset placement and index placement. Other aspects are the script files themselves, which include database data definition language, which is nothing but DDL, and data control language, which is nothing but DCL statements. ETL, extract, transform, load, is the most complicated process in a DW and BI environment because it must coordinate the population of all data warehouse target databases. The purpose of the ETL process is to extract source data from the disparate sources and move it into the data warehouse target databases while simultaneously standardizing and integrating the data. The most important aspect of ETL design is the source to target mapping document showing all data transformations. Next, we will see about data warehouse build. A proven and sound data warehouse development methodology combined with a collaborative approach with the goal of giving ownership of the BI application to the business people has proven to be most successful. By building a more self-service oriented data architecture, the user community becomes incrementally empowered and productivity rises. Implementing the backend ETL process is usually done using an ETL tool such as SQL Server Integration Services, which is nothing but SSIS. Depending on the condition of your source files, that is integrity, location and history of the file, the complexity of the required transformations and the functional limitations of the ETL tool, you may have to write some custom code to enrich the ETL tool functionality. Next, let us discuss about BI architecture and modeling. Standard procedures, guidelines and conventions must be in place during the BI modeling phase. Establishing modeling policies is crucial for the DW and BI components and the relationship among them to function properly. The BI model gives way to the business applications, which are the business processes that access data from the data warehouse through reports, ad hoc queries and business dashboards. Next, project planning. Ongoing management of the independent components of the BI initiative should overlap all phases of the data warehouse project to derive the highest business value. Often, companies are internally working on multiple projects in parallel, making it a challenge to manage the DWBI project while respecting timelines, milestones and realigning requirements with changing business needs. Until you know what the data warehouse effort will be, you cannot create a project plan and commit to any deadline. Next, we will see about post implementation. After the new DWBI project is implemented in production, the project team performs a post implementation review. There is an opportunity to streamline the development approach by practicing more process reuse, avoiding redundant tasks, improving communication, improving estimation methods, identifying gaps in infrastructure and defining critical success factors for the next project. Next comes data warehousing physical design. During the logical design phase, a model for the data warehouse consisting of entities, attributes and relationships is defined. The entities are linked together using relationships. Attributes are used to describe the entities. The unique identifier UID distinguishes between one instance of an entity and another. The following diagram explains the difference between logical design and the physical design. During the physical design process, expected schemas are translated into actual database structures. At this time, we should map the following: entities to tables, relationships to the foreign key constraints, attributes to the columns, primary unique identifiers to the primary key constraints, unique identifiers to the unique key constraints. The following section contains the following topics: number 1, physical design structures; number 2, about views in data warehouse; next, about integrity constraints in data warehouses; then partitioned indexes in data warehouse; about materialized views in data warehouses; about dimensions in data warehouses. First, let us discuss about physical design structures. After converting logical design to a physical design, we need to create some or all of the following structures: table spaces, tables, partitions on tables or index organized tables, indexes including partitioned indexes, views, integrity constraints, materialized views and dimensions. Next, we are going to see about table spaces in data warehouses. A table space consists of one or more data files which are physical structures within the operating system we are using. A data file is associated with only one table space. From a design perspective, table spaces are containers for physical design structures. Table spaces need to be separated by differences. For example, tables should be separated from their indexes and small tables should be separated from large tables. Table spaces should also represent logical business units if possible, because a table space is the coarse granularity for backup and recovery or the transportable table spaces mechanism. The logical business design affects availability and maintenance operations. Next, we are going to see about partitioning in data warehouses. In partitioning, it allows tables, indexes or index organized tables to be subdivided into small pieces. Each piece of the database object is called partition. Each partition has its own name and may optionally have its own storage characteristics. From the perspective of the database administrator, a partitioned object has multiple pieces and that can be managed either collectively or individually in the partition. This gave the administrator considerable flexibility in managing a partitioned object. However, from the perspective of the user, a partition table is identical to a non-partition table. No modifications are necessary when accessing a partition table using SQL DML commands, database objects. In these tables, indexes and index organized tables were partitions using partitioning key, a set of columns that determine in which partition a given row will reside. For instance, a sales table partitioned on sales date using a monthly partitioning strategy. The table appears to any application as a single normal table. However, the DBA can manage and store each monthly partition individually, potentially using different storage tiers, applying table compression to the older data or store complete range of older data in read-only table spaces. Basic partitioning strategies used in data warehouses. Actually, three fundamental data distribution methods that can control how the data is actually placed into the various individual partitions are: first one is range. The data is distributed based on the range of values of the partitioning key. Toward a date column as the partitioning key, the January 2012 partition contains rows with the partitioning key values between 1st January 2012 and 31st January 2012. The data distribution is the continuum without any holes, and the lower boundary of the range is automatically defined by the upper boundary of the preceding range. Next, we will see about list. The data distribution is defined by the list of values of the partitioning key. For a region column as the partitioning key, the North America partition may contain values Canada, USA and Mexico. A special word default partition can be defined to catch all the values for the partition key that are not explicitly defined by any of the list. Next, we are going to see about hash. A hash algorithm is applied to the partitioning key to determine the partition for a given row. Unlike the other two data distribution methods, hash does not provide any logical mapping between the data on any partition. There are more approaches for partitioning. First, interval partitioning, an extension to the range of partitioning that enhances manageability. The partitions are defined by an interval providing equi-width ranges. With the exception of the first partition, all the partitions are automatically created on demand when matching data arrives. Next, partitioning by references. Partitioning for a child table is inherited from the parent table through a primary key foreign key relationship. Partition maintenance is simplified and partition wise joins enabled. Next, virtual column based partitioning. It is defined by one of the above mentioned partitioning techniques, and the partitioning key is based on a virtual column. Virtual columns are not stored on the disk and only exist as metadata. This approach enables a more flexible and comprehensive match of the business requirements. Using the above mentioned data distribution method, a table can be partitioned either as a single or composite partition table. we will see about single or one level partitioning. A table is defined by specifying one of the data distribution methodologies using one or more columns as the partitioning key. For instance, consider a table with number column as the partitioning key and two partitions less than 500 and less than 1000. The less than 1000 partition contains rows where the following condition is true. The condition is 500 less than or equal to partitioning key less than 1000. We can specify the range, list and hash partitioned tables. Next, composite partitioning. Combinations of two data distribution methods are used to define a composite partitioned table. First, the table is partitioned by data distribution method 1 and then each partition is further subdivided into subpartitions using second data distribution method. All subpartitions for a given partition together represent by a logical subset of the data. For instance, a range hash composite partition table is first range partitioned and then each individual range partition is further subpartitioned using the hash partitioning techniques. To conclude, physical design takes the data warehouse implementation closer to the hardware. Physical design activities may be grouped into steps. The importance of the standards cannot be overemphasized. Adopt sound standards during the physical design process. Other performance improvement schemes that are part of the physical design include the following: data partitioning, data clustering, data processing, creation of summaries, adjusting referential integrity checks, proper setting of DBMS, initialization of parameters and use of data arrays. Thank you.